Hello everyone, I'm Tong. I'm here to present our paper, Non-Revisiting Coverage Task with Minimal Discontinuities for Non-Redundant Manipulators. The problem is to generate a non-revisiting coverage path on the surface of the object, satisfying that the coverage path minimizes the number of end-effector lift-offs. Previous work modeled the NCPP problem into an optimal design strategy of colors, but it considered only a small set of task constraints, and the cells are only simply connected. By efficiently discarding the equivalent design of the cutting path between different colors, there are only a finite number of different cellular decompositions. So the first contribution of this paper is to consider the necessary conditions of the NCPP problem we modeled as a topological graph. Here we omit the details and only show an example. When people consider different kinds of criteria of the valid configurations, the shape of the topological graph may be strange, and there may be non-simply connected cells, as shown in this figure. If we visualize the translational manipulability of configurations, we can see that they are not monotone on the surface. So even if we choose the same manipulability measure, if we use different thresholds, we will have totally different topological graphs. So the second contribution of this paper is to propose a multi-stage iterative solver for solving cells with all genus. Similar to the previous works, we notice 5 kinds of equivalent cellular decompositions that can be safely disregarded in solving genus 1 cell. The first one is that if the cutting path doesn't connect both the inner boundary and the outer boundary, then we can temporarily remove the inner part and put it back after solving the outer part. The second equivalence is that the inner part and the outer part is equivalent, so we can solve them separately. The third one is that it is unnecessary to consider the cyclic cutting path, because they perform the same as the acyclic one. The fourth one is that we needn't consider a single cutting path, because the two sides of the cutting path are the same cell, which are impossible to have different colors. The fifth one is that we only need to consider two cutting paths, which divide the original genus 1 cell into two simply connected subcells, because all other cutting paths can be seen as further divisions of the subcells. In conclusion, we prove the finite solvability of the genus 1 cell. For genus 2 cell, we prove that we can put in the two inner boundaries one by one. Each time we put in one inner boundary and create two cutting paths. Finally, we may do further cellular decompositions in each of the subcells. Here we need to prove that it is unnecessary to put the inner part outside the cutting path. So this is the sixth equivalence. Using the mathematical induction, we prove that all genus cells are finitely solvable. For genus N cell, each time we put in one boundary and create two cutting paths to transform the cell into simply connected subcells. Finally, the genus N cell will be divided into N+1 simply connected cells, which we have already known that they are finitely solvable. The most representative experiment in this paper is covering a Mobius strap, which is a classical non-orientable surface. The least number of discontinuities in fully covering the Mobius strap is 1.